So, welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we did in the last class. So, in the last class we looked at the differences between piezoelectrics and piezo, pyro and ferroelectrics, and the underlying basis was crystallographic basis. So, as we said that a piezoelectric material is something which is non-centrosymmetric, except 432, all the non-centrosymmetric point groups are piezoelectric, and then pyroelectrics are those which are non-centrosymmetric plus they have a unique polar axis. As a result, they have a spontaneous polarization. And then ferroelectrics are which are non-centrosymmetric plus unique polar axis plus reversibility of polar axis. So, as a result, you can look at the Venn diagram where piezoelectric is the biggest class of non-centrosymmetric materials. Some of the piezoelectrics are also pyroelectrics, and some of the pyroelectrics are ferroelectrics. So, ferroelectrics is the most restrictive class of materials. So, out of these 21 minus 432, that is the point group which are non-centrosymmetric. So, 21 PGs except 432, and then here you have 10 of them, and here less than 10. Okay. So, this is what we did, and we also looked at then the piezoelectric tensor. So, piezoelectric effect is basically coupling between mechanical and electrical response. So, by mechanical we mean it is mostly elastic in nature. Okay, it is elastic in nature, and this is, so we have a direct piezoelectric effect. In direct piezoelectric effect you have charge density produced as an outcome of applied electric field, applied stress, not electric field. Okay. So, this is the direct piezoelectric coefficient whose units are in Coulomb per Newton. And then we have indirect effect where we relate the strain with respect to d k I j, and your stimuli is basically the electric field, and this is your indirect coefficient which is essentially in meter per volt, alright, and this is strain. And so, as a result you can see that this is this. So, now if you look at this d I j k, this is a third rank tensor, right. A third rank tensor will have 3 to the power 3, which means 27 components. But since we know that stress and strain are symmetrical tensors, so as a result you have x I j is equal to x j I, and small x I j being equal to small j x j I. So, as a result when you expand it, so d I j can be expanded in the form of matrix. So, let us say d1, so initially you will start with d11, then you can go to d121 and so on and so forth. So, you write for d211 and then similarly d311 and so on. So, when you do the matrix expansion, you can see that so if you have d I j k, this will be equivalent to d I k j. Okay. So, as a result, because of this correlation between the stress and strain, you will reduce the number of components to. So, basically something like D123 will be equal to D132, right. So, all these components will become equal. So, we can say that total number of components reduced from 27 to 18. So, this is what, and they can further be reduced by crystal symmetry depending upon the type of crystal and so on and so forth. So, essentially, and we also looked at the examples of materials. So, examples such as silicon oxide is the best known, one of the best known and simple piezoelectric. Then you also have zinc oxide. Then materials which are ferroelectric is always so things like PZT or PBTiO3 or BATiO3. These are all ferroelectric which are naturally piezoelectric. And then of course the polymeric materials like PVDF, polyvinylidene fluoride, CH2, CF2, they based materials, they are also piezoelectric in nature by the virtue of being ferroelectric in nature. Now, let us move towards what we call as pyroelectric materials. Pyroelectric effect. So, pyroelectric effect, as we say that basically pyro means, this term pyro will mean it is related to temperature, and electric will mean it is related to electric field. So, basically pyroelectric effect is nothing but coupling between thermal and electrical parameters. Okay. So, as we said that the requirement for a pyroelectric material is that it should be non-centrosymmetric and it has a polarization. So, when this pyroelectric material is subjected to a temperature difference delta T, as a result it has certain charge density change in, you can say, since it is polar it will always have charge density, right, but as you change the temperature there is a change in charge density. So, when you apply a gradient delta T, which means it results in change in delta PS. So, change in the PS, which is delta PS, and this delta PS is nothing but the, you can say, surface charge density that you have induced as a result of making temperature change. So, we can correlate a value called as pyroelectric coefficient which is, let us say, small pi, and this small pi is nothing but change of psi, which is a vector with respect to temperature. So, this is pyroelectric coefficient pi, which is del psi divided by del T, where Ps is the spontaneous polarization, and we know that it is a vector, right. It has a unit of Coulomb per meter square. So, as a result Pi will have unit of Coulomb per meter square per Kelvin, and this is also a vector. Okay. Alternatively, you can also write that induced charge density let us say di, this is related to delta T and this is related to delta T by small pi, and this is nothing but delta psi, right, the change in the spontaneous polarization that you observe upon psi upon applying a thermal gradient. So, these materials, as we said, they are non-centrosymmetric, necessarily non-centrosymmetric and necessarily polar. Okay. So, basically all the ferroelectric materials are pyroelectric materials, and most of the commercially available pyroelectric materials are nothing but ferroelectrics in themselves. So, now let us move to another effect which is which you must know, is called as electrostriction. Okay. Electrostriction is very much similar to piezoelectric effect, except that and it is basically, you can say, coupling between electrostriction, right. So, coupling between, you can say, its strain and and electric field, same as piezoelectric effect, except that piezoelectric effect occurs in non-centrosymmetric materials, whereas electrorestriction occurs in all dielectric materials irrespective of symmetry. So, it is an effect that occurs in all dielectrics irrespective of symmetry. So, this is where when you make piezoelectric measurement, it is important to distinguish between what you are seeing as electrorestrictive effect and the purely piezoelectric effect. And so the electrorestrictive strain that is generated by applying an electric field is depicted as Xij. This is electrorestrictive strain. This is depicted as Xij is equal to electrorestriction coefficient Mijkl into Ek into El. It is a vector, so you can't write Ekl, which will become a tensor. So, you have to write Ek and El. So, you can see that this is a 4th rank tensor. Okay, and this is basically electrorestrictive coefficient. All right. So, you can also write in terms of polarization. So, we know that polarization is related to electric field by susceptibility, right, P is equal to chi into E. So, if you can do that transform, then alternatively we can say Xij can be written as Q Ijkl into Pk Pl, where these are the polarization vectors. So, instead of writing in terms of electric field vectors, you can also write them in terms of polarization vectors, and these polarization vectors are related to so polarization vectors are related to electric field by susceptibility, right, because we know that susceptibility is nothing but P divided by epsilon naught E, right. So, basically the proportionality constant will be susceptibility. So, you can sort of write this as M can be related to Q as Mij, let us say Mn is equal to chi Km into chi Ln into Q Ijkl. So, this will be the electrorestrictive effect. So, we are not going to get into details of electrorestriction, but basically it is something which is present in all the materials, and it can be present in addition to piezo electric effect in the materials. Okay, and sometimes piezoelectric effect in ferroelectrics may also be interpreted may also be explained as sort of electrorestriction which is based on spontaneous polarization. So, there is a possibility that polarization that is present in the material that gives rise to electrorestriction, which is manifested in the form of piezoelectric effect. So, this is basically a brief introduction to the tensor notation of these typical properties, which are, so what we have looked at is we have looked at dielectric properties, okay, we have looked at elastic properties, and we have looked at piezoelectric properties, and we have looked at pyroelectric properties, and finally we looked at electrorestriction. Okay. So, these are all basically vectorial tensorial properties which are related to the stimuli, which could be stress, or it could be the electric field, it could be delta T, temperature difference. So, basically we have these proportionality parameters which are in the form of stiffness, in the form of susceptibility, in the form of piezoelectric coefficient, in the form of pyroelectric coefficient, or in the form of electrodestruction coefficient, which are all second rank, third rank, or fourth rank tensors, depending upon the properties they correlate. Now let us do a little bit analysis of these properties in terms of thermodynamics. Okay. So basically what we want to now look at is how these properties are correlated to each other, because we have seen, when you have a thermal gradient, you have a polarization change. Change in polarization will lead to change in the electric field. As a result, you will have you may have strain. So all these thermal properties, electrical properties, elastic properties, they are all correlated to each other. So we must understand the coupling between these properties. So coupling between electrical, mechanical, and by mechanical we mean elastic, okay, and thermal and for this we will establish what we call as a first thermodynamic basis. Okay. So we have seen that, for example, in a piezoelectric effect you have direct piezoelectric effect, right, when you apply a stress and you get a response in terms of change in you can have polarization, for example, induced polarization. Similarly, in the converse effect, when you apply electric field you will get strain, right, and this and then pyroelectric materials, when you apply delta T you get delta P, which is nothing but D. So and it is important, because these properties are correlated to each other, we need to evolve formalisms so that they are useful in making us understand how experimental determination has to be done. So for example, when you make piezoelectric measurement, let us say you make piezoelectric material for a free material, okay. Free material means it is ready to expand, contract in other directions freely. There is no external constraint on it. But let us say, so this is a free material, okay. But let us say you have a material in this form. You have a substrate which is, let us say, silicon, okay. On the silicon I have put a layer of, let us say, zinc oxide, all right. Now in this case this becomes a constrained media, right, because the strain in the thin film is going to arise as a result of clamping with the substrate, because they are atomically bonded with respect to each other. So in this case, when you apply electric field, you have a strains of different kind, they are all free strains, whereas the strains that are generated in this case are going to be determined by boundary conditions, how the material is clamped with respect to substrates. So as a result, it is important to understand the effect of various variables on the calculation of these parameters, so that we exactly decouple various effects. For example, whether the piezoelectric strain is because of stress only, or is it also because of, does it also have a contribution from substrate induced strain, or because of differences in coefficient thermal expansion between film and the substrate, and so on and so forth. So basically you would like to decouple these effects, and to decouple these effects and understand them, and also it also allows you to choose parameters, which parameters to allow, which parameters can be allowed to change, and which parameters should be kept constant, okay. So that is what it helps us to determine a formalism in terms of, let us say. So basically these are all thermodynamic expressions. So thermodynamics, I am sure you have general knowledge of so basically you are aware of terms, I assume that you are aware of terms such as G, which is Gibbs free energy, U is given as internal energy, right, S is given as entropy, and H is given as enthalpy. Okay, these are certain thermodynamic parameters, and we all know that G is equal to H minus Ts, or it could be equal to alternative form is if it's a constant volume process, then it could be U minus Ts, depending upon where you are looking at constant pressure or constant volume. So, you can have various scenarios, but we are not going to get into thermodynamic discussions, but I hope that if you do not know thermodynamics, then I would like you to go to any basic books on thermodynamics. There are plenty of books. For example, you can read this Thermodynamics of Materials by Gaskell. There is a book by thermodynamics by Lupus. Then you can also look at some classical thermodynamics. So, thermodynamics of materials is slightly different as compared to thermodynamics of mechanical systems like engines, etc. So, but the terminology remains the same. The concept of entropy, free energy, enthalpy, that remains the same. So, you can go through any basic books on thermodynamics if you are not aware of the thermodynamical parameters. So, let us say, so thermodynamics are 3 laws, as we know: first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. So, using first and second law of thermodynamics, we can write that a reversible, let us say U is internal energy. So, you have a so you have a elastic dielectric, okay, which is subjected to, let us say, a tiny strain. So, it experiences a tiny strain, let us say dx, it experiences a dielectric displacement dd, okay, and as a result, and it also has a change in entropy, which is ds. So, for such a system, the change in the reversible change in the so we can write the reversible change in the internal energy of this system can be written as du is T ds plus x I j into d small x I j plus E I d d I. So, this is the strain, this is the change in the dielectric displacement, and this is a change in the entropy, where T is the temperature, X is the capital X I is stress, and E I is the electric field. So, most of our measurements, as we see, although we make temperature dependent measurements, but at each temperature certain measurements are made. So, most of the measurements that we make, electrical measurements or dielectric measurements, they are all isothermal in nature. So, and so temperature is generally kept as constant, whereas other variables are, you can have electric field, or you might apply change in stress. So, these are the variables that these are the parameters that you independently vary. So, as a result, the independent variables that we have in the first, so in this case the first slide, the independent variables is, so what are the variables here? The independent variables are S, Xij and Di. So, but however, since the measurements are made in the form of by keeping electric field as a variable or stress as a variable. Temperature is kept constant, but it could also be a variable. So, we generally make our measurements in this fashion. We would like to change these parameters. So, right now we have a set of parameters, entropy, strain and dielectric displacement. We would like to transform them to electric field, stress and temperature, and these are all related to each other. So, they are not sort of independent of each other. So, for this what we call as, we make a transformation in the thermodynamic parameters, and this is basically done by what we call as Legendre transformation. So, Legendre transformation, which if you have done basic engineering mathematics, you would know what Legendre transformation is. So, as a result, when you apply this transformation, the free energy function free energy is G, basically Gibbs free energy function, can be written as G is equal to U minus Ts minus capital X ij, small x ij minus Ei di. Okay. This is capital G. Now, if you want to look at the differential of G, that is the free energy change. So, dG will be equal to du minus Tds minus sdt minus xij d of small xij minus of small xij d of xij minus of Ei ddi minus of di into dEi, right. So, this is the free energy function that I get in the form of all the parameters. So, we include, this is the internal energy, and these are the terms which lead to change in the these are thermodynamic changes, right. So, basically this is the entropy term, and you can take rest of the terms U minus, this is the next term, which is basically the net internal energy, you can say. So, now if you do the subtraction of du, we know what du is, this is du term. So, when you subtract du here, you will get rid of TDS, you will get rid of this term dxij, and you will get the term consisting of ddi. So, what we will get is basically dg will be equal to minus of sdt minus of small xij d of capital Xij minus this is ij, and then minus of di into small d Ei. This is what we will get in terms of the change in free energy. So, the change in free energy is related to minus of sdt minus of small xij differential of capital Xij minus of di into change in electric field. So, now we have stated the change in free energy in the form of parameters that we vary, okay, and from this we will calculate the properties independently. So, we have run out of time now, we will stop here. What we have done is basically we have looked at the pyroelectric properties in this lecture, and also we have started a thermodynamic basis to understand the properties, and before we get into material applications and some other features. Thank you very much.